Hi, we're starting the second lecture of this week. We're still in the micro-canonical ensemble. Is this on? It's working. Micro-canonical ensemble. And so far we have seen two different models for this ensemble. We are seeing the Einstein model for solids, and we've seen the two-state model. And the basic idea is always the same. The assumptions of micro-canonical ensemble is that the probabilities are all equal. Okay? Meaning all the different states of the system are equally probable. This means that in order to compute something, we need to compute the number of states for a given energy. The energy is a constant. Okay, so for any given energy, so for any given energy, we need to compute the number of states. Okay, number of states. And the moment that we know the number of states, we can compute, or we define that the entropy is simply a k-Boltzmann log of this omega, okay? And this is our state function, because afterwards, whatever we know about entropy is valid. For example, the relation that 1 over the temperature is simply the derivative of the entropy with respect to energy. We've used U for energy. Okay, let's continue with this setting, right? And we have seen two examples. And the way that we calculated this number of states is basically was a combinatorial approach. Okay? So what we're going to do today is to continue this approach for yet another example. Which is termed the Polymer Model. Okay. So polymers, basically, for us, are long molecules that are combined out of a series of smaller molecules that we call a monomer. Okay. What exactly is going on over there? So there are some chemical bonds between the different monomers. They're attached to each other, right? There are different models of how this polymer behaves. How the density or the length of the monomer depends on the number of the different monomers. So all of this is a polymer. Each one of this is a monomer. Okay. And there are a huge number of experiments, specifically nowadays, which are termed pooling experiments. What people do, they can attach this molecule, this polymer, to a molecule or to a surface, then catch part of this molecule or part of this monomer, polymer by optical tweezer, for example, or some other experimental technique, and then we can pull on this monomer. Okay, by pulling on this monomer, okay, for example, it's attached to a wall over there. Okay, we apply a force on the other side. Okay, and by studying of what happens to the force, how hard we need to pull, and how it actually affects the length of the polymer, we can study different microscopical properties of the interaction between different polymers. Specifically in Bar Ilan, the group of Yuval Guerini, they are doing, well, at least did, huge number of such experiments. Another type of experiments that are not exactly pooling, but you can attach a specific molecule. This is very nice. You can attach a specific big molecule on the top of this polymer, okay, and then you can track this molecule in a microscope, like for example a confocal microscope. Basically you pin this specific using something like a quantum dot. You pin this molecule, it reflects light. Okay? You can collect the photons that are coming out of this molecule. Then you can track this point in space as a function of time. And then you can see, for example, that this molecule performs some sort of a random motion. Okay? This random motion, by studying the properties of the random motion, you can get backwards and predict something about the different properties of the polymer itself. All right. So this is what's done in experiments. It's not really old experiments. We're talking about last decade. Okay. Now, how we can theoretically at least make some sort of predictions about what's going on with such a long molecule. Okay. We can start, as a chemist will, we can basically say, well, it's a very complex problem. I will need to describe all the different chemical bonds. I will need to describe almost everything about this polymer. The root of this approach is very computational, because eventually, if we include all the information about all the different molecules inside our model, we are becoming pretty much lost, and the only thing that is left is to run simulations, molecular simulation, and it's a very difficult task. Okay, but if we don't want to use this approach, we want to use a more physical approach, which is more minimalistic. We need to assume something very naive, something very basic, and hope that we will basically not throwing away too much of information about the microscopical processes that are going on inside, but still gain some information about what's going on. For example, the Einstein model. What was the Einstein model for solids? Is that you have atoms, and those atoms do not interact with each other, but they are still vibrating. We know that this approach will fail for low temperatures, but for high enough temperatures, it actually works pretty well. Okay? And what it means, we can study and understand the physics that there are much less interactions for high temperatures, and the atoms almost do not interact with each other, at least for temperatures that are high enough. The same we can maybe understand for the polymer. If we will assume something very basic about this model, about this molecule, maybe we can study something about what's going on and what determines generally the properties of the polymer. Maybe not the specific bonds and the specific chemical connections, because for this, statistical physics in general is not enough. You need to assume something very specific. But general properties you can deduce by using very simple models, very simple assumptions. So what are our assumptions for this type of a polymer? So first of all, we are saying the following. Each monomer for us is a bond, okay? And this bond can be either parallel, so if this is the y-axis and this is the x-axis, okay? So each bond or each monomer can be parallel either to the x-axis or to the y-axis, okay? So in general, when we are plotting this polymer, what we have in mind is a bunch of different bonds that are connected somehow to each other. The length of each bond is exactly this, it's equal. So we can continue this drawing and draw our okay, and here we apply our force F. So this is our polymer. We start with a certain point, okay? It somehow fluctuates in space, right? And eventually we are pulling on this polymer on the right hand side, okay, with some force F. Yes?
First of all, in the model you suggested, it can also be in the x-axis backward, forward.
Okay, so you're saying yes, we can do something like this. Pretty much fine. Okay.
Okay.
Yes?
What about the z direction?
Two-dimensional, okay? So one dimension is too simple because one dimension is only one string. We add only two dimensions. But in general, yes, I can assume that there is also a z direction, and my monomer can be parallel to y, parallel to x, parallel to z. No. So we will see something basically two-dimensional. What we are going to see that the moment we add additional dimensions to the problem, some nice results are actually occur due to the possibility of this polymer to fluctuate in space, right? But addition of the z direction, at least for this polymer, does not affect almost anything. Other models of polymers that are using something like which is called a random walk, they do depend on the dimensionality of your problem. But for this guy, it's more than enough the two-dimensional case. Okay, so what we are talking about here, we're talking about micro-canonical ensemble. So we need to define the energy of the system. U is the energy of the system. And the energy of the system somehow depends, right? It somehow depends on on the orientation of each monomer. Okay? So we're going to say the following. Each monomer that is either oriented parallel to the x-axis, and I don't care if it's in the positive direction of the x-axis or the negative direction of the x-axis, the energy is 0. Okay, of this monomer. Each time the monomer is perpendicular to the x-axis, basically parallel to the y-axis, the energy is epsilon. Right? This is similar in some sense to this two-state model that we used on Sunday. Okay, so this is basically it. This is all the model. Oh, one additional thing is n is the total number of monomers. Okay, so remember it's a micro-canonical assumption, so we assume that all the different states of the system are equally probable. Okay. What we are going to do now is somehow deduce what is the different number of states of this system, where for each monomer the energy is described by this rule, either 0 or either epsilon. The energy of the system is constant and it equals U, and the total number of monomers is N. So how one approach such a problem? So first of all, we know that N is the total number of monomers. Nx plus is the number of monomers that are oriented in the plus x direction. Okay, so all of those guys. This is Nx plus. Nx minus is the total number of monomers that are oriented in the minus x direction. Okay. I can say also that I have ny plus oriented in the plus y direction. Okay. And ny minus oriented in the minus y direction. Okay. Now, the moment I define those guys, nx plus, nx minus, ny plus, ny minus, I can say what is the total number, of the different permutations of, or what is the total number of states? This is the total number of permutations, okay, such that I can choose nx plus, nx minus, ny plus, ny minus, such that the total number is n and the total energy is U. Okay? So basically, omega of U is n factorial divided by nx factorial, ny factorial, and nx plus factorial, ny plus factorial, and x minus factorial, and ny minus factorial. Okay? So on Sunday we had only 3 factorials, now we have 5 factorials, so the equations are going to be even uglier than before. But this is not enough, because we need to somehow introduce physical constraints. For example, what are the physical constraints that we have? That nx plus ny plus nx minus plus ny minus equals to n. Okay? And I also want to insert in my model something that is physical, something that I can observe an experiment and relate to it. For example, what is it? I want to describe it in terms of the length, okay, of the monomer in the in the x direction, and also the length of the polymer in the y direction. Right? I can operate with nx and y, nx minus and y minus. Yes, I can do that, but I prefer, okay, to describe it with something that I can observe in experiment, Lx and Ly. Okay. So let's write down all the different constraints that we have. So first of all, n equals simply nx plus ny minus plus ny plus nx minus. Questions? No? All right. What else do we have? We have that nx plus minus nx minus equals to Lx. Okay. The same I'm going to do with ny plus minus ny minus equals to Ly. And I also have an additional constraint, which is ny plus ny plus ny minus equals to u divided by epsilon. This last constraint comes from the idea that the only energy, positive energy, that is coming inside this model are only from the monomers that are perpendicular to the x-axis. Okay? How many of them I have inside? Ny plus and ny minus. Okay? Here, this is some sort of simplification. I could make things much more complicated by starting to say, well, if this is in this direction, this also contributes energy epsilon 1, in the other direction epsilon 2. There's also dependence on if I'm along the y plus axis or the y minus axis, but it is simple enough and it's actually interesting enough, or ugly enough already. Okay, so what is the next step? The next step is, instead of using nx and y and x and y over here, to use all of those constraints inside the definition of the number of states. Okay, so what we are getting from those equations, we need to solve them, okay, and describe what is nx plus, ny, nx minus, ny plus, ny minus in terms of Lx, Ly, n, and u divided by epsilon. Okay, so we are having nx plus, nx minus, ny plus, ny minus, okay? Those are our variables that appear over here, and we need to transform them into n u divided by epsilon, Lx, Ly. Okay? This is simple enough, because this is a set of four linear equation. Okay? So the result is nx plus equals 1/2 n minus u divided by epsilon plus Lx. Nx minus equals 1/2 n minus u divided by epsilon minus Lx. Ny plus equals to 1/2 u plus Ly. Ny minus equals to 1/2 u minus Ly. Okay, so we're now ready to write down this ugly function. So the omega of u is n factorial divided by this ugliness over here. So 1/2 n minus u divided by epsilon plus Lx factorial. 1/2 n minus u divided by epsilon minus Lx factorial. Multiplied by 1 divided by 1/2 u plus Ly factorial multiplied by 1 over 1/2 u minus Ly factorial. Okay, and what else do we need to perform? We need to say S is equals K Boltzmann, a logarithm of all of this thing. Okay, omega. Okay, so we are going to take the logarithm of this guy. We are going to obtain 1, 2, 3, 4, 5 different logarithms of factorials. Okay, so we have 5 logarithms of factorials. Each logarithm is transformed by the usage of the Stirling approximations into 2 terms, and eventually this will produce a formula with 10 different terms. Hooray, hooray, but this is really long, so I will write down the final answer for the entropy. Okay. We already know how to transform using the Stirling approximation, and we know that the Stirling approximation works extremely well even when n is not so big. Okay. Eventually, after doing this, easy to show. Easy to show. This is long. Okay, I'll write down whatever is written in my notebook. So S equals to K Boltzmann n log n minus 1/2 n minus u plus Lx. Let's write it down. S divided by K Boltzmann. Log of 1/2 n minus u plus Lx. U divided by epsilon, thank you. U divided by epsilon minus 1/2 n minus u divided by epsilon minus Lx log of 1/2 n minus u minus Lx, u divided by epsilon. This is first line. Second line, third line, minus 1/2 u divided by epsilon plus Ly, not K Boltzmann, a log of 1/2 u divided by epsilon plus Ly minus 1/2 u divided by epsilon minus Ly log of 1/2 u minus u divided by epsilon minus Ly, and hopefully it is. A long and not so interesting formula. Now I want to relate this S to some physical quantities. Okay? How do we do that? So first of all, we know the relation that we already used, that 1 over T is ds du. Yes? Ny plus is the total number of, so it is u divided by epsilon, u divided by epsilon, first of all. Yes, u divided by epsilon plus Ly. Okay, so where were we? So we know that 1 over T equals ds to du. Okay, so this is going to be our first equation. But we can do a little bit better and say the following. So we will do this, don't worry. We need to take all the different derivatives, etc., etc. So even for such a simple model, the micro-canonical ensemble, it's a very ugly and not so nice, let's put it like in this way to derive stuff. We will see that when we use canonical ensemble, everything becomes much more simpler. Okay? Why is it so ugly? Because we needed to count all the different states. This is a problem of counting. Okay? We will see that when we are, instead of counting, performing some sort of integrations and use specific assumptions of canonical ensemble, things become much more easier. All right, so this we are going to use. This will provide for us some physical intuition, or physical equations at least, because temperature is something that we can control. This polymer is immersed in some liquid, and there is a temperature of the liquid, okay, or the temperature of the environment. But we can also say the following. Remember this equation from thermodynamics, dE equals to TdS plus tau y dLy plus tau x dLx. Okay, we had all different forces. The force multiplied by the change of the extensive variable. Okay, so if we apply some force and we increase the size of the polymer by dLy, okay, the energy is increased. The same goes for dLx. So what we know from this equation, we can say the following, that ds is 1 over T dE minus tau y divided by T dLy minus tau x divided by T dLx. Okay? So basically, ds dLy equals to minus tau y divided by T. And ds dLx equals to minus tau x divided by T. So this is how physical quantities come inside our system. We counted, we obtained this equation of state, and then we use thermodynamical equations that we know from thermodynamics or whatever, the relations between entropies, energies, etc., and we can obtain different physical quantities. What is the force that is affected, extracted on the polymer? Okay. What is the temperature? The only thing that we need to know is how to take derivatives of those guys over here, which is fairly simple. It's really long, but fairly simple. All right, so what we see is that we take this guy and we start to take the different derivatives. I won't bother you exactly how to take the derivatives because they are fairly simple. We have multiplications of polynomials or linear functions by logarithms. Very tedious, very long, but simple enough. Even I managed to do it. All right, so ds dly equals to k Boltzmann divided by 2 a log of u divided by epsilon minus ly divided by u plus ly. What is the force? So I don't have the picture over here. So what is the force that we applied on this polymer in the y direction? There was such force? No, there was not such force. So this should be 0. Okay? This should be 0. That provides us with an answer that Ly equals 0. Okay? The moment Ly equals 0, we have a log of u divided by epsilon divided by u divided by epsilon. It's log of 1. Log of 1 is 0, all right? So this is the force. Our force in tau y is 0 because we know it's 0. We have not applied any force. And we know that the fluctuations in the y direction of the length of the polymer, okay, so what is the y direction? We started at this point. It have done something like this, and then we applied force. Eventually the force was only in this direction, tau x. This is something that we know because we are experimentalists and we know with what force we pulled on this polymer. The total fluctuations in the y direction from the start to the end, there can be fluctuations over here, but the average fluctuations, okay, from the starting point to the ending point is simply 0. Okay? And this is clear because the system is symmetric. Okay? I have the equal probability to be up or equal probability to be down. Okay? Because my energy when I'm up or my energy when I'm down is exactly the same energy of each given monomer. Right? So this is why, due to symmetry, we need to obtain this result that Ly equals 0. Okay, we can do the same for Lx. There it is different. Okay, so first of all, let's write it down. Tau y divided by t with a minus sign. So we are doing the same for minus tau x divided by t equals to ds dlx. It equals to k Boltzmann divided by a, not a, I don't have a, k Boltzmann divided by 2, a logarithm of n minus u divided by epsilon minus Lx divided by n minus u divided by epsilon plus Lx. And this all equals to minus tau x divided by the temperature. Okay? We can turn it out in the following sense that e to the power of minus 2 tau x divided by k Boltzmann t equals to n minus u divided by epsilon minus Lx divided by n minus u divided by epsilon plus Lx. Okay? So we related some quantities such as the force that we applied, the length in the x direction, so the how we pulled on this polymer, the number of monomers, they're all tied together.
I think tau x doesn't have a
Yeah, because I used that the length of each monomer is 1. Okay? You remember I've said that n minus L something something equals to Lx. So there was an assumption that the length of each monomer is simply 1, and this is why the units are simply okay. Okay, we can use this equation over here. So 1 over t ds du. I don't write again all the different derivations of how I've taken the derivatives of this guy. It's simply long and ugly. So 1 over t ds du, okay, equals to k Boltzmann divided by 2 epsilon, a logarithm of n plus Lx minus u divided by epsilon, plus a k Boltzmann divided by 2 epsilon, a logarithm of n minus Lx minus u divided by epsilon, right? And I also have minus k Boltzmann divided by epsilon, a logarithm of u. Okay? Now I can tie this up all together because this is a k Boltzmann by 2 epsilon, k Boltzmann by 2 epsilon, and I can say this is a minus k Boltzmann by 2 epsilon multiplied by a log of u squared. Okay? Then I will have this multiplied by this divided by this. Okay? So eventually I have e to the power of 2 epsilon divided by k Boltzmann t equals to I have n plus Lx minus u divided by epsilon multiplied by n minus Lx minus u divided by epsilon. All of this divided by u divided by epsilon squared. So let's see. We have this equation, and we have also this equation, right? And by using this, we actually can get rid of the dependence of the u from the system. Okay? Okay? I can use this equation or this equation in order to determine what is u divided by epsilon, and then substitute this relation inside this equation backwards. Okay? All right. So when I do this, I eventually, so I combine equation number 1 and equation number 2, and I eliminate the dependence on the energy. What I obtain is that Lx divided by n equals to hyperbolic sinus of tau x divided by k Boltzmann t divided by hyperbolic cosine of tau x divided by k Boltzmann t plus e to the minus epsilon divided by k Boltzmann t. Okay. So now I can see that how this extension of the polymer, this is Lx, how it depends on the temperature, okay, and the exerted force. Temperature I can control, the force I can control, I can maybe measure different number of monomers that I have inside the system, right, by using this formula. What is the interesting stuff that I can obtain out of this? Okay. So first of all, I can calculate what is dLx to d tau x. Okay. So by how much my polymer extends when I apply force. we'll know this quantity as the elastic modulus, right? It's 1 over k. You know the Hooke's law, F equals k delta x, depends on the direction. Okay, so F divided by k is delta x. So dl to df is 1 over k, basically the spring constant. Okay, so we have a polymer. We look on this as some sort of a spring, all right? We look on this on some sort of a spring, okay, and we ask ourselves, when we apply force by how much is, or what is the impact on the size of the polymer. This is something, again, that is interesting for different kind of materials and measurable quantity. So we can take this derivative. It's now fairly simple. We only have their hyperbolic sinuses and cosinuses. It's nothing terrible over here. Okay. So when we do this, we obtain that dlx to d tau x equals to n divided by k Boltzmann t 1 over 1 plus e to the minus epsilon divided by k Boltzmann t. Okay, so it only depends on what? On the energy of each monomer, monomer and the temperature. First of all, we can measure this quantity. The moment we measure this quantity, we can, and we know that what is the temperature of the system, okay, we can basically penetrate microscopically and say, well, we assumed some sort of an additional energy that each monomer has in order to be oriented perpendicular to the direction with where I pull the polymer. Okay? So we can somehow understand and see that we can calculate and measure epsilon for a given system, which is nice. But what is actually nicer in this system? This is the elastic modulus. The elastic modulus, okay, increases or decreases when I increase my temperature? I increase my temperature. This goes down or up?
This one goes down.
This one goes down. Okay. So my elastic modulus is basically going down, decreases as I increase my temperature. Now, I don't really know if you learned the theory of elasticity, but in the theory of elasticity for a spring constant, okay, the elastic modulus is actually going up when I increase my temperature. What happened over there? Sorry? This is like elastic modulus for a spring. Okay? For a spring, I increase my temperature. It's easier to stretch it. Okay? I take a spring. Where is my spring? I take a normal spring. Okay? I heat it up. It's much more easier to stretch it right now. Okay? I obtain that I've taken this polymer, I've calculated the effective spring constant of this polymer. Let's assume that my polymer is a spring. I heat it up, and it's much more harder to pull on it. Right? I haven't added any force. I haven't changed the interaction energy, the epsilon. It's still the same. Where this phenomena came from? Wait a minute. Why it's easier to pull on a hotter spring? Because it's hotter and the interaction between the different molecules is more loose. Okay, what do you wanted to say? Yeah. So, but this is related to your previous question. Dimensionality. What happened over here? The moment I permitted this polymer to fluctuate in another dimension, it's less favorable, right? What is the most favorable position, right? The most favorable position is that all the different monomers are exactly parallel to the direction that I'm pulling. Okay, why? Because this is the zero energy, right? We talked about it. The preferable situation is the minimal energy. But what we have seen, what actually happens, is we permit some of the monomers to be in a different situation, to be not parallel but perpendicular to the original direction. So you say, well, it only decreases the energy. Increases the energy. It's not preferable. You're right, but we are counting states, right? And the moment we permitted this polymer to fluctuate in this direction, okay, maybe those states with different monomers that are perpendicular are less favorable, but there are a huge number of them. Okay? So what happens to the system? We heat it up, it starts to explore more and more states. It has more states to explore. Those states are less preferable, but their number is huge when compared to one single state where all the different monomers are in the same direction. Right? So when I'm increasing the temperature, I have many more states that this polymer can wrap around itself, basically, right? And when I start to pull, it's strangled, okay? It performs knots. Why there are such knots? I don't see any knots in my simple model, but the idea is exactly the same. The moment I permitted it to fluctuate, I permitted it to explore different states, right? This created effective entropic forces. They're not real. They're not there because I've now introduced some new energy, interaction energy between the different monomers. No, it's only came up from the fact that now all those different monomers can wrap around themselves. Okay? This is a less preferable state, but there are many of them, right? So the system is somehow wandering in all those different states, and as the temperature rises up, there are more states that it can explore. Okay? And it basically is somewhere in between all the different states that are less preferable, and when I'm trying to pull, it's wrapped around itself. So the entropic forces, they are the ones that are creating the decrease of this elastic modulus. Okay? I'm not expecting this result based only on the energetic assumptions. Okay? But from statistical assumptions, okay, what is the statistic here? That I have many different states, and I'm not only counting the most preferable one. Right? My system is exploring all the different states, and most of the time it won't be sitting over here. It will be sitting in some phase, part of the phase space, which is strangled because there are a huge number of states, and this creates additional effective forces. All right, so we are stopping here, and we still have something small left for the micro-canonical ensemble, but next lecture we will start something much more nicer, canonical and grand canonical ensembles. Thank you.